Welcome, everybody. I'm Chris Carberry, CEO of Explore Mars. Welcome to, I believe, the fifth Humans to Mars webinar called Mars Mission Architecture Advancing Tech for H2M. This is a series of webinars we're doing leading up to the Humans to Mars Summit. We hope that it'll take place in late August, early September. More details on that in a second. Before I introduce our moderator for today, I have a few short announcements. First of all, join us next week on Wednesday, May 13th at 3 o'clock Eastern Daylight Time for a webinar called The Overview Effect. We'll be featuring Frank White, the author of the book, The Overview Effect. That'll be moderated by Mary Liz Bender and Ryan Chalinsky, both from Cosmic Perspectives. If you want to register for that, you can go to our website at ExploreMars.Org. So that should be a spectacular one. We also have a couple of other great webinars coming up over the next few weeks. The week after that, we will have a session on the 19th of May. We will have a webinar called the 30th Anniversary of the Hubble Space Telescope, and we will have John Grunsfeld on, and Matt Kaplan will be moderating that session as well. So we look forward to that. And then 2 days later, we'll have Star Trek personality and director Jonathan Frakes, who will be talking to us about the collaboration between the entertainment industry, space community, and STEM education. So we have a really great lineup of webinars coming up. And if you haven't checked it out yet, Explore Mars is co-hosting Janet's Planet Online Astronaut Academy every day at 10 a.m. Eastern Daylight Time. Janet's put together a wonderful program for students, but even if you don't have kids, it's worth checking out. She does a wonderful show every day, so definitely check that out. Just a reminder, as I mentioned earlier, we hope the Humans to Mars Summit will take place on August 31st through September 1st at the National Academy of Sciences building. You know, we're still hopeful that we'll be able to do it live. We'll send out updates, but each time before these workshops or these webinars, I also like to thank many of our sponsors for the Humans to Mars Summit. Today, I'd like to thank Aerojet Rocketdyne, Lockheed Martin, Northrop Grumman, ULA, Paragon, MDA, National Institute of Aerospace, and many others who I'll be mentioning throughout this webinar series. So thank you to everybody who sponsored H2M and these webinar series. And speaking of that, thank you to everybody who has made donations as well. It is very helpful. As you can imagine, running these webinars is not free, and it's sometimes not cheap. So thank you to everybody who's been able to donate. But if you haven't, if you'd like to help us out, even a small amount, please go to ExploreMars.Org and please donate. Anything you can do would be greatly appreciated. At any rate, so I'd like to introduce you to our moderator for today's session, a longtime friend of Explore Mars, Matt Kaplan, the host of Planetary Radio. So Matt, thanks for leading today's session. This one's a great one. So Matt, thanks.
Absolutely. Thank you so much, Chris. I'm thrilled to be back doing work once again for our sister organization, Explore Mars, and sure hope that Humans to Mars conference takes place as planned. A little late, but still a spectacular event for us to attend in Washington, D.C. So welcome, everybody. I really am thrilled to be back for my second of these outstanding live events from Explore Mars. I am with the Planetary Society, and that is, as Chris said, where I've been host and producer of Planetary Radio for the last 17 plus years. And of course, hope that you'll check us out over there as well. The Life on Mars event that I moderated began this series, and that's available, of course, from Explore Mars. You can find it at ExploreMars.Org. Really terrific conversation with Penny Boston and Jim Green for that. That was followed by shows about dealing with the isolation that astronauts will increasingly face as we go into deep space. And most recently, I think, saving our planet from climate change through space resources. Now we're going to take up a topic that is well below the radar for many, including even space fans like you and me. And yet it may be more responsible for the success of missions than any other factor. You know what you get when you Google mission architecture? Try it. The first things you'll see are the beautiful Spanish missions that run the length of California. So scroll down. Eventually, you'll get to the kind of mission architecture we have in mind today. What is it? And how will it enable us to send humans to Mars and bring them back safely? This is without a doubt, I hope the panelists will agree, the greatest spaceflight mission architecture challenge of all time. Fortunately, we have three outstanding mission architects who will help us understand why this field is so critical. And we'll also explore how that Mars mission may take shape in the next decade or two, hopefully not more than that. My one and only slide today, which is going to be popped up by our director, Wade, here, gives you an idea of mission architecture from half a century ago, actually even a little bit before that. This is how to get to the moon and back with humans in 27 easy steps. And this is, even at this level, merely the highest level overview of what mission architecture is all about, at least as I understand it. But that's really why our experts are here with us today. And so let's go ahead and we'll start talking with them. And you can drop that slide, Wade. Thank you. I want to be able to see my, my intro here. Up first today, and she will also be the first to present to us a little bit later, is Najud Moranci. Najud is a systems engineer with extensive background in human spaceflight and spacecraft at NASA's Johnson Space Center. She is chief of the Exploration Mission Planning Office. That means that she and her team are responsible for engineering, designing, developing, and integrating NASA's human spaceflight portfolio beyond low Earth orbit. And these missions include planning for the Orion Multipurpose Crew Vehicle, which you'll be hearing more about, the SLS, or Space Launch System, that big rocket, Exploration Ground Systems, Gateway, formerly known as the Lunar Gateway, and Human Landing System. She also spent years providing critical planning and other support for the International Space. Najud, welcome today. I'm so glad that you were able to join us for this great discussion.
Thanks for having me. I'm looking forward to it. So that was a great intro.
Thank you. Tell us a little bit about yourself and your work, and then in a few minutes after we've met the other panelists, you'll be able to tell us a little bit more about why mission architecture is something you love to do.
Yeah, so in terms of mission planning office, so I really have a fortunate team, and one of the really cool things about our office is we're doing everything from Artemis 1 right now through the Mars analysis. So when we talk mission architecture, one of the big pieces to it is how all these systems tie together. And you've got rockets and in-space vehicles and landers, and everything has to work together. So it really is a system of system challenge. And we get to see it from cradle to grave, from what's going to fly next year all the way out through 20 years ago. Those studies influence what you do today. So that's really the fun part of mission analysis, and my job in particular leading this office.
And you've been at this for a while. Would you say that what you've been doing all along has been mission architecture? Because it certainly has other elements, actually many elements involved with it.
Yeah, no, I would say no. I'm more of a recent mission architecture convert, coming out of the systems engineering world, because I started my career in guidance, navigation, and control, systems engineering, and pulling all those systems together through the Orion program development and all of these things. Because when you really talk mission architecture, everything has to work together, and the contingencies and the drop-off points. So it's more than just the trajectory of getting somewhere. While that is the foundation of what you need, all of those things have to come together. So for me, mission architecture is that systems engineering of how do you put it all together and keep the crew safe as you go there and come home again.
As you know, because I posed this question to you and our other panelists that we're about to meet, this relationship between systems engineering and mission architecture is one that all of you have already addressed. And so I suspect that will come up a little bit later as well. So again, thank you for joining us, and we'll be back with you in a moment. But let's go now to meeting Joe Cassidy. Joe Cassidy is Aerojet Rocketdyne's Executive Director of Space Programs in Washington, D.C. operations. He has oversight of strategy development and architectures for future space and launch systems. He's heavily involved in planning for human missions to the moon and Mars. He also serves as Executive Vice President of the ExploreMars Board of Directors. He has nearly 40 years of experience with rocket propulsion and mission and systems analysis. A Purdue grad, he recently collaborated with 3 professors from his alma mater to, to author a new textbook titled Rocket Propulsion. Why don't you just call it rocket science, Joe?
Yeah, thanks for the plug.
You're welcome. So what brings you here today?
Oh, so I got started looking at planning for Mars because I wanted to say my interest in Mars probably goes back to being born in the late 50s, growing up in the era of Apollo, having a mom who put me down in front of the TV to watch even the Mercury launches. I think I saw every Gemini launch. I saw every Apollo launch. And so, you know, I think I couldn't do anything else. I was sort of, you know, in the right time frame. I was at Purdue when the shuttle launched, and about 15 of us piled into 3 cars and drove from West Lafayette to Florida nonstop, so we'd be there to see the launch of the first space shuttle with John Young and Bob Crippen. It's in my blood, I think, and in 1986, I was fortunate enough to go to a conference in Washington, D.C. called the Mars Conference. A lot of really, you know, big name people were there, Carl Sagan among them, and it just was something that fascinated me. The company I worked for at the time, which has been subsequently bought and now is part of Aerojet Rocketdyne, built the Viking lander engines. So, you know, I think I've always seen Mars as the thing that really defines my career. And I'm very hopeful that by the time that ends, in not too many more years, we're able to say we've put humans on that planet.
You and me both. I was sitting on the floor in front of our black and white TV watching those Mercury launches, and I was at the other end of that first shuttle mission on the dry lake bed when Bob and John came floating in. What a spectacular, spectacular moment. Thank you, Joe, and I look forward to hearing your presentation in a few minutes as well. So let's get to the third of our panelists today, and that is Tim Cheehan. He is the Space Exploration Architect at Lockheed Martin. What a great title. He leads a multidisciplinary team of engineers who figure out how to help astronauts and robots visit the moon, asteroids, and the red planet. He used to be the Orion system architect for the company, helping to create that spacecraft that is designed to carry men and women into deep space. He's been with Lockheed Martin since 2002, also working on both human spaceflight and commercial communication satellite teams in such areas as optimal trajectory design, mission analysis, subsystem development, and systems engineering. There's that phrase again. Tim, welcome to you. And sounds like you are yet another great person to have for this discussion of mission architecture.
Yeah, thanks, Matt. And, you know, when I think about as a kid, my dream job and what I wanted to do when I grew up in a much more simplistic way, this is it, to be able to be, you know, have all the responsibilities and the freedom to look towards the future and understand how are we going to accomplish these missions? How are we going to send people to the moon? How are we going to send people to Mars? And, but sometimes, you know, once you get into college and all of that, and you kind of lose sight of that really big picture, and you don't know how to get from graduating with an engineering degree to being a, you know, dreamer of the future. So now my background in communication satellites and trajectories really kind of prepared me for the big picture. And then when the Orion program started, I knew that, hey, I had forgotten about my human spaceflight dreams, and it's time to get back to that. Spent a great time on Orion, really learning how to do it and what it takes at every detailed level of how to design the spacecraft to go to deep space. And then at the end of my time as being Orion system architect, this opportunity came up to join our advanced programs team. And really have that responsibility. And the reason we do this work is to understand, you know, how are these missions going to be put together? What technologies do we have right now? What technologies need to be developed? And also to keep our eye on, because these things take multiple systems, what does Orion need to do to be ready for its most challenging missions today, and to understand where the evolution path of each system as it builds up, Orion, SLS, Gateway, HLS, Mars landers, Mars cargo vehicles, all of those things. How does that all work together? So pretty excited.
Fantastic. Very exciting stuff. And I'll say again what I quote from my boss, the science guy. You can hear the passion, beauty, and joy that all three of these panelists feel for their work. And that's what partially why we're talking about going to Mars and the mission architecture that's going to help us get there. Slight departure for a moment, Tim. I hear that Orion spaceship is pretty much ready to go, ready to take humans at least as far as the moon.
Yeah, and our Artemis 1 spacecraft, which is an uncrewed test flight, we're on track to hand that over to NASA later this year. So that's pretty exciting. The first crewed Artemis 2 vehicle is in full production, and we've started on Artemis 3, which will take the crew to the moon to go climb into the lander and go down to the surface. So yeah, full speed ahead.
Can't wait. All right. Najud, we go back to you because we're going to let you take over and make a little presentation. Of course, later we'll open this up for general conversation amongst ourselves. And then, of course, all of you watching today, and thank you again for joining us. I see we're nearly 250 strong now. It'll be your turn. And you probably know that you can submit your questions at any time. The great Janet Ivey of Janet's Planet is going to be threading through these and consolidating them for us and feeding them back to us. And we'll be getting to that before the end of the hour. And hey, if the questions keep coming in, I know that all of our panelists are prepared to stick around for a few extra minutes beyond our nominal 2 o'clock stop time. Nominal. Love to use that word, right? Najud, I turn it back over to you.
Hi, thank you. So we'll just go straight into slide 5 here. So really, one of the first questions you always talk about is why the moon before Mars? And, as was announced last week, was really exciting. 3 systems were picked for a lander system development, at least to start evolving. And really, we're going back to the moon because we need to work on building our hardware and system skills and really setting the foundation of that open infrastructure to mature systems to eventually go to Mars. So all of the things we're doing, this isn't a dead end at the moon. This is a road that goes through the moon onto Mars. So, and if you go to the next slide, as you can see, as you push farther out from the Earth, these challenges get harder and harder. When we're in low Earth orbit on the space station, it's just a few hours to get home. And your speed's at 17,000 miles per hour to re-enter. When you come back from the moon, it goes up a good 7,000 or 8,000 miles per hour on that entry, and even more if you did a direct entry from Mars. And even while the speeds can be linear, the heating is exponential. So all of these challenges are just more of the reasons why, as we push farther out, it's harder and harder to make the systems continue to work and to have all the aborts and contingencies that you need to support humans. So next slide, and you're all very well aware of some of those challenges for humans in the system. So when you send robots, you get around some of these very easily because you don't have to worry about isolation and the mental health of a robot, as we're all experiencing currently, more so than normal with the coronavirus response. So we're getting our little taste of being astronauts right now. But all of these things are the systems that you have to incorporate into human mission design, which makes it so much more challenging. Humans need all these things. We need to have backups and safeties so we can keep them safe. And especially one of the hard parts of human mission design, even for the moon, is how do you turn around and have aborts? You never have just one mission, you have thousands of missions. Because if you go to the moon, you need to abort for any failure, that's a different trajectory than you were planning for when you left. So all of those challenges of integrating things together continue to be the big hazards and the opportunities, though, to make our systems even better over time. And I'll stop there and pass it on to Joe to talk a little bit more specific.
Thank you, Najud. Joe, let's go right to you.
All right, so we can go to my first chart then. Actually, we can go to the next one.
Good title, though.
Yeah, that reminds me who I am and who I work for. I pulled this one out of the Wayback Machine, but I thought I would start here because I wanted to tell people, this isn't new. This is something that we've all been dreaming about for quite a while. So this is actually a chart that I found many years ago when we just had become part of Aerojet Rocketdyne, or actually Aerojet, before we were part of Aerojet Rocketdyne. And this is from the Aerojet General Corporation. It was produced in 1962, believe it or not. And I just love this chart because what it has on it, and it's a typical chart from back in the days before calculators and computers. There's a whole lot of ways graphically to represent this information. And you can see here, it's a mission planning chart for all of the planets in the solar system, almost. I guess they didn't include mission to Pluto on there, but there are things like human missions to Mars and Jupiter included on here. And there's so many things about this chart. I love it. It even has a budgetary aspect to it. But I really just wanted to say, for everyone, this is part of why I think this is such an exciting time, because we're beginning to realize the dreams that these folks have been, myself included, have been looking at for all these many years. And a couple of years ago at one of our Humans to Mars conferences, we were all talking at one of the breaks, and somebody said, it's been 20 years away for the last 30 years. And for the first time, I really feel like we're inside that 20-year window and the clock is running. So we're getting close. I'll go to the next chart. So a couple of things, I'll just amplify some of those points that Najud made. When you're going to Mars specifically, you're kind of constrained, unfortunately, by the relative locations of the planets, and the Kepler sort of rules everything. And so we have a couple of constraints that we have to sort of try to fall within. We try to go at the most opportune times, and that's about every 2 years or so. And there's a couple of different ways we can go that group into these two broad categories, the opposition class and the conjunction class. And right now, I think we're again thinking about this because we do have those problems with the humans that, they have a lot of needs and demands, and the consumables that they need to stay alive, the time that they're out there in the deep space environment, which has both the microgravity aspect as well as the galactic cosmic rays, the radiation aspect. We try to shorten that time as much as possible. So I just sort of showed these two, and they both have advantages and disadvantages. I think the key thing is we have to have the right amount of data to make this choice. And it's hard right now because our data sets are sparse. We've only ever sent 12 human beings out beyond the Van Allen belts into true deep space, and they were only out there for a very short amount of time. We're building the database up now on the space station for microgravity, but we still don't have the real good information about the radiation, and that's both for the humans as well as the systems. And Najud was exactly right. Robots are a lot easier than humans, but all systems get affected by that deep space environment. So we really need to test things out in the true environment. So we'll go to the next slide. I just wanted to spend a minute and talk about how, this is really kind of a classic systems engineering trade-off. And one of the things I loved as I took my systems engineering courses was how they broke it down into a real simple thing. You have kind of cost. You'd like to keep the cost down as much as possible to keep the project, feasible and make it work. You have schedule. You've obviously got these launch windows and things that I was talking about with getting to Mars. You've got to fit within that. And then you've got the technical aspect. And I just showed on here the external forces that kind of drive you in different directions. And if you think about that little ball in the center as, you could almost look at this like one of those games where you're tilting it and it's rolling back and forth across this board. And so those external forces are driving the ball in different directions. And that's what we're always responding to. We're trying to keep the cost inside the box. We're trying to keep the schedule reasonable. So, you know, if it stretches out too far, we lose the political will, or we miss a launch window, or the mission duration itself is too long and it's not going to meet what the human health requirements will allow us to do. If we wait too long to get the right technical solutions, you know, the perfect technical solution may be 30 years in the future. I don't want to wait that long. I'd like to see us land on Mars in the 2030s. So these are the kinds of things that we're always balancing. And the goal is to find that balance and keep that ball right down the middle, centered. Okay, go to the next one then, please. So I mentioned the data earlier, and I think this is a real key with the Artemis program now. We need to reduce the risk. As you mentioned, you know, the abort scenarios and things like that. One of the problems with going to Mars is you don't have a whole lot of time and availability of abort windows. Once you're going, you're going. So by going to the moon and doing a lot of this stuff with the Artemis program, we can learn about a lot of the things that we're going to need to know for going on that really long journey before we take that jump to go to Mars. And I mentioned a few of them here. Some of the things that we're looking at now with Gateway, where we can actually put vehicles together out there in deep space. Gateway is going to use high power solar electric propulsion, or SEP. That's going to be something that we can really use to great advantage in going to Mars, because one of the things we really have to do is to support the humans and to really do a Mars mission. It's a big logistics challenge. You have to send a lot of stuff over a very long distance. So having something efficient like solar electric propulsion will help us do that. And then there's things we're looking at with Artemis, like putting a crew on the Gateway, keeping them there for a while, and then sending them down to the surface where they'll work in a reduced gravity environment. But it's similar to what a crew going through a 200-day transit to Mars and then landing will have to do. So we can actually do some pretty effective simulations at the moon. There are some things we'll have to go to Mars to do, or we'll have to test them in other environments, but we're looking at that too. And a couple of key things that we've got to really work on are entry, descent, and landing for big payloads. With the Curiosity rover and now with Perseverance, we're talking about roughly 1,000 kilograms, about a metric ton. We've got to go up by about 20 times for the human mission. So that's a big jump. And then things like making propellant or oxygen off of the surface or from the atmosphere of Mars. That's something else that's a big enabler. So we're looking at all this, we're gathering the data, and I think with the information we'll get out of Artemis, that'll help us from tipping that board over too far, because when we do that, we end up getting a game reset and we have to start all over again. Okay, next slide, please. Next slide, thank you. So the bottom line is, when we do all that and we look at these things, and I think Najud made a really good point earlier, you end up with a lot of different pieces, and you have to make sure all those pieces work together effectively. So I just share this chart for everyone. This is kind of one of the ways we're looking at it at Aerojet Rocketdyne. Obviously, the SLS and Orion play key roles. The lunar experience and working at the Gateway is going to be something that's important. And then we see a kind of a split crew and cargo approach, where we can ship a lot of cargo out to Mars on the slow way, like we do with ships here on Earth, but it can get there and be pre-positioned. And then we'll send the crew more effectively with something like a nuclear thermal or a chemical rocket that can get them there as rapidly as possible. So that's just a little bit of our view of the world right now, and I'll turn it over back to you, Matt.
Thank you, Joe. Boy, I suspect I was not far off the mark when I said we are looking at the biggest mission architecture challenge of all time in getting humans to Mars and back. And I'll let you folks comment on that further later if you choose. Joe, I hope you've got a bumper sticker that says Kepler rules. Can we go back, Wade, to Joe's slide number 9 for a moment? Because I love the history of space exploration and space development. And this slide, I want this for my wall.
I can make that available through the Explore Mars website if you'd like.
Would you do that? And I'm hoping, I don't want to put anybody else on the spot, but I'm sure that we have many participants out there who would love to have access to your slides as they can be made available for proprietary and other reasons. But this slide is just spectacular. I have behind me in the bookcase the Life Science Library, including Man in Space, that has the Nova rocket. Yes, Man in Space from early 60s, not Humans in Space. And there's the Nova, which, I was looking forward to after the Saturn V. Never heard of the Sea Dragon, but the other one I want to point out is on the far right, that Taurus space station, or actually it looks like a vehicle to get places. Yeah. Look at the fine print, zero gravity gymnasium. You have to take care of human needs, right?
Right.
Okay, again, thanks, Joe. We're going to go on now to the third and last of our presentations. So, Tim, take it away.
All right. Well, and before we start looking at slides, I wanted to, talk about the kind of things that we have to take into account when we're doing planning. And Joe, I really liked your triangle of competing forces, and it's always a challenge not to, push so hard that the ball falls off, right? And the other thing that I've learned as we've started to do these architectures is, there's all the technical things, there's all the trajectory things, and, Kepler rules, and there are things that you can't change. And from a technology point of view, there's always this push and pull of, well, do I wait for the big advancements in technology like nuclear thermal propulsion, or do I go now? And how do you got to be prepared for both ways and make your decisions about, okay, we're going to take this technology we have today because we know it works, but this thing is very intriguing and we want to move forward. And also to have the flexibility to incorporate new technologies as you move along. But more than just technology, there's other things that are very important. And one of those is operations. The actual execution of the mission with the ground support and the crew interacting with multiple vehicles is so important. And a lot of what we need to do at the moon to get ready for Mars has that, it comes from the operational point of view. And we've got lots of great experience with ISS and the cargo vehicles and the crew vehicles and spacewalks and repairs and science. And that is just as important as some of the technical stuff to be able to not only do your nominal mission, but be prepared for every kind of contingency. And then there's also the political and the stakeholder aspect of mission architectures and making sure that there's a lot of different points of view and stakeholder things that people care about. And with human spaceflight, it's never one thing about why we explore. There's exploration to explore, there's exploration to achieve great science, there's exploration to inspire the world, to take up STEM. There's all kinds of different reasons, and they're all very important. But when we think about going to Mars and how difficult that is, and Wade, if you could pull up slide 16 for me. So those historical views are awesome. I love those, and they have a different way of kind of talking about the data. This is our version from Mars Base Camp from a couple of years ago of the recurring missions and the kind of logistics that we need to do, and the mixtures of all the different systems, cargo, crewed vehicles, and all of that. And it's important to be able to think about these types of missions. And one of the things about Mars is that, as you do your chart, the jump from 3 days to 3 years for a mission is a huge jump. And one of those things is that the crew is now on their own for the most part. And so the systems that we needed to design needs to have the reliability and the redundancy, and perhaps even the dissimilar redundancy, so that if one thing goes wrong, the crew has lots of different options to figure out what the problem is and to go fix it on their own. And that's one of the, that operational challenge mixed in with the vehicle design is one of the things that really excites me about the great work we're about to do. So let's go to chart 14. Eugene and Joe both talked about how Artemis enables Mars. But some of the other things that in that buildup to our horizon goal of being on Mars, operations, infrastructure, the science that we do at Mars and on the moon, the human experience, what is that mission going to be? All of these things we've started at ISS, and the moon is going to give us another, big step up, another big ladder in working all of these different problems during a real mission and producing the hardware for that mission. That experience is invaluable, and we can't even really predict all the things that we're going to learn, but we know that's going to be important. And another thing that I'll note is that as we keep in mind this journey that we're on, that building upon the shoulders of giants and building systems that evolve is really important. So go ahead to the next slide. And this is from a few years ago where we were thinking about, well, from a crew perspective, the two key systems for Mars are the lander and the Mars Transit Vehicle. And the Gateway and the HLS landers are really the first step that is necessary before we get to the Mars systems. And so as we lay out a way to make these systems more capable and more and necessarily more complex to support crews for longer and longer durations, we see how we can start from where we are today to where we need to be for Mars. And we can actually probably even have overlaps here as we develop the next system. We'll test it at the moon, then we'll test it at Mars. So I'm pretty excited about the future ahead of us, and I'm really excited that we're taking those next steps with HLS. And I can't wait to be on the surface of the moon, because I know the surface of Mars is not far behind.
Wow. Thank you, Tim. I remember, and I think it was a couple of years ago, at the Humans to Mars conference from Explore Mars, it was the first time I was introduced to this ambitious Lockheed Martin base camp plan. And I just wonder if you have anything that you might say about how that plan and the work that went into it, including the system architecture thinking that went into it, or mission architecture thinking, is still appearing as we move forward with Artemis. I mean, where really any kind of thinking about mission architecture, even if things go in a somewhat different direction, contributes to the goal.
Oh yeah, sure. So, the two main elements of Mars Base Camp at a high level are the main Mars Base Camp vehicle. NASA calls it the Mars Transit Vehicle, and its applicability to, starting with the Gateway, the human habitation piece, the closed life support piece. Those are still the same problems that we're dealing with. And then on the lander side, our idea for Mars is a single stage ascent and descent vehicle. And we know that will take a little bit of work. But the HLS vehicles from the announcement last week, there's a couple of different ways to do that. But you can some of them are one stage from the beginning, and some of them are starting with multi-stage and can build up to one stage. And so that really fits in well.
Yeah, three very interesting concepts announced from those three companies picked for further development of HLS, the Human Landing System. Thanks again, Tim. I was just reviewing there some of the great questions that a lot of you are submitting, which Janet is collecting for us, and we will be getting to those very, very soon. But maybe just a couple of more questions that we'll cover before we do that. And as I said, we may go a little bit beyond the 1 hour nominal length of this program today. Fortunately, all of our panelists have consented to stick around, but I'm sure we will not get to all of your questions. They will be kept, though, and reviewed And I know that Explore Mars is hoping that all of them can be responded to as we go through the days ahead. It seems from listening to the three of you, you know, there are still voices out there that say, why are we wasting time going to the moon? But do any of the three of you have any doubt that getting to our nearest neighbor first and proving things out is going to be a really important step in designing the system architecture that will get us to Mars and back? Nishud?
There's no doubt in my mind, right? Even as we're having the conversations and people have looked at the HLS systems and the proposals, right? A lot of people go, well, why don't you just do what Apollo did? And Apollo was awesome and it was an incredible challenge, but they were really still very limited on where they could go on the moon because of the performance demands that come along with Kepler and the rules for getting there. And you can't even take Apollo and go and do South Pole exploration like we're trying to do. And just getting the companies and the architects and everyone to start considering how hard the South Pole challenge is and staging something out like the Gateway for years to be able to demonstrate that operations and maintenance can be performed. You know, those are all precursor steps. When you say, well, let's put something in Gateway orbit, it can sit there for several years, and the Mars mission is several years long. So all of these things are actually proving those Mars systems. So there's no doubt in my mind that we need to take this incremental step, because you can't just say we're going to build everything, put the crew on it, and send it on its merry way with no test demonstration in the first place. Right? Going from theoretical to real missions involves the test and validation of your systems as you go. And really the moon is the test and validation of Mars.
Joe, Tim, anything to add?
So one thing that I'll note is that the Artemis program has that sustained operations as part of its objectives, which is very different than Apollo. And that is so important because for Mars being so far away, having all of that, the sustained operations down, the in-orbit elements, eventual propellant production on the surface of Moon and Mars, those are very key things. And so, you know, to your original question, there's no doubt the Moon is very important. The only thing that we need to keep in mind, though, is to always keep moving forward. You know, all three of us on this call, our horizon goal there is Mars, and so we need to do all the testing and validation at the moon, and then it's time to move on to tackling that next challenge, that next ladder of Mars.
And I'll jump in and just add to Matt. Recently in November, we had a workshop, for Explore Mars sponsored a workshop that we've had a series of Fording Mars workshops, Achieving Mars. We call them different things as we've evolved them. But the focus of this one was actually looking at the Artemis program and looking at what is it we're going to need to know to be ready to take this jump to go to Mars. And our group that I was part of, we basically brainstormed about 85 steps in the whole process, as Nishud and Tim have referred to. You know, we've got to get the crew out there. We've got to land, we've got to get back off the surface, and we got to come back home and get safely back down to Earth. So we took all that, broke it down into about 85 steps. Each one of those, and some of these were, you know, technical things like propulsion. Some of them were operational things like docking vehicles or roving on the surface. You know, all these kinds of pieces of that overall big picture. And we found that, I think it was, you know, more than 90% of them had value from the various pieces of the Artemis program in burning down some of that risk by doing these things that we're doing at the moon. So I think that was a big validation of the idea that we can learn from going to the moon, the things we're going to need to do to go to Mars.
Fortunately, Administrator Bridenstine of NASA has said, at Humans to Mars, he said it on my show and many other places, make no mistake, we're going to Mars. And in other words, the moon is not the final destination. I said I wanted to bring up systems engineering, and that's the question I posed to all three of you before this program began. There are so many factors that have to mesh in good mission architecture. But what I've learned fairly recently, in large part because of reading a great book called Spacesuit, is about the importance of systems engineering. Is it a more important factor, I mean, than the other things you have to consider? And you've talked about some of these factors, but how do you fit them all together? I mean, there's so many different areas of expertise to come up with, to design good mission architecture. Najut, let's go back to you first.
Yeah, I mean, this is really, you know, this is my background, right? I have degrees in this, and this is my job, is making all of these pieces fit together. Systems engineering is the art of solving the complex problems with all the competing demands, and mission architecture is just the biggest, most visible piece of systems engineering, because you have to do it with multiple systems, with systems of systems. And I think Artemis is a really good example of, once you set out with a mission architecture, you set out with the best of intentions, but as you work through the design, you run into constraints and issues, and there's always this iterative process. So really, for what we have to do a lot at work is keep iterating on the design as you go. So where you started with one concept, you'll run into an issue. So, okay, well, let's tweak it and do this. And so it's that art of continuing to tweak things all along. And so you're balancing those constraints. And a lot of, like, currently the moon mission architectures, even for Artemis 1, there's a lot of balance between sunlight and, you know, eclipsing. How long is that constraint versus what is the performance on the rocket, and how long can the systems operate, and how big is your engine burn? There are so many constraints. You're always trying to balance these things coming in. And it's really that integrator, that systems engineering job, to make sure you still have a viable mission when you're done. So that is the big challenge.
I'm sorry. Joe, I saw you nodding enthusiastically there.
Oh, yeah. Oh, what Najut said was perfect. I'll throw in a little anecdote that I learned. I actually think I learned this, Tim, from somebody at Lockheed Martin when I was working on a project with you guys. But the systems engineer, their job is, you've got all these different discipline engineers, right? You've got the thermal guy, you've got the structural guy, you've got the propulsion guy, and you know, they all see the problem very differently. And the job of the systems engineer is to take all those inputs and figure out a compromise that makes everybody equally unhappy.
Yeah, I always joke, if everyone likes you, you're not doing your job as a system.
You're not doing your job, right?
I hear the same thing from principal investigators on robotic missions. So,
yeah.
Tim?
Yeah, and I definitely agree. Everyone equally unhappy. That's the goal. And one of the most important parts of the system engineering process is the definition of interfaces between all of the different elements. And sometimes it's, you know, the mechanical interface between the vehicles, but sometimes it's the interface between the crew and their vehicle, and how they communicate between and control their vehicle. And sometimes it's interfaces amongst the different ground control centers. And so it could be electrical or mechanical, or data or communications or fluids. And the best system engineers are the ones that can pull all of the different disciplines together and get those interfaces defined as early, as clearly, and as simply as possible. And that really goes a long way to making the whole system work well together. And often in just defining those interfaces, that you very quickly figure out, oh, this interface is going to be very complex, and we got to put some emphasis on that.
And I'd even add a little bit to Tim, because even once you take those mechanical interfaces, you go up a level. Well, you've got a rocket and a spacecraft and a lander, and now you have to negotiate between programs. So some problems mean this program has to spend money that they didn't really need to, but that might be the most efficient solution across the architecture. So it is a delicate art of balancing not just the technical, but that programmatic cost and schedule that Joe brought up earlier.
I think of the human factors involved as well. You compare this to a robotic mission where you might say, okay, the engineer says, yes, we can accelerate, or we can land with this many Gs. And then the human factor person says, well, that's great. I'm glad the vehicle will survive because the astronauts inside won't. How do you integrate human factors like that into mission architecture design work?
Tim, do you want to take that one first?
Sure. So human factors, or the environmental requirements for the people, are just as important as any other system. And so they need to be defined and well understood. And this is a case where we've got so much data all the way back to the Mercury program that that part of it, the environmental part and the life support part, that is very well understood, and we've got disciplines all across both companies and NASA and around to do that. But also human factors often means the interfaces between the people and the vehicle, both on the ground, people putting together the vehicle or operating the vehicle, and the astronauts flying the vehicle. And there's an art and a science there to how do you display information so it's quickly understood, and how do you sort of provide the right controls to be able to quickly assimilate all that information and tell the vehicle what it should be doing. And I'm excited about the future here, because now things like artificial intelligence and talking to your spaceship and those sorts of things are actually possible, not quite possible in space today, but soon. And so that's another exciting opportunity.
I'm being selfish. I would love to just keep the three of you for myself and my questions, but we are now well into the time, at least 4 minutes in, to when we are supposed to be turning to the other brilliant folks out there who have joined us, the other Martians out there, maybe I'll say, for this discussion. And it's going to be, as I said, difficult. We're not going to get to all of these, but I'm just going to pick and choose from among those that Janet has been collecting for us. Najud, this is one that is directed to you, but for any of these folks, all of you are welcome to respond. This came to us from Dustin Bergstrom. There are companies like some of yours that design and build spaceflight vehicles, labs, satellites. What about habitats on the Moon and Mars? Is right now the time for bold architecture, engineering, and construction firms to begin designing those habitats? And as you probably know, there have been some really interesting competitions recently. I think we have Vera Mogliani actually as one of our participants, and she leads that very innovative design competition for building habitats on Mars, some of which are way out there, at least as far as the orbit of Mars, but some of them are much more down to, I guess I should say, down to Mars. Is this part of, I guess it would have to be, right, part of mission architecture? You got to build houses.
Absolutely. So this is absolutely the right time to be making those considerations, because NASA currently has what's called the Next Step BAA, broad area announcement of habitat design already in work, and Lockheed is one of the participants, and that is, how do you put a habitat on the surface of the Moon? How do we build that deep space 3-year Mars mission habitat for space? Those things are currently happening all over the place, and that's part of the value of, we need to make progress. So even doing short demonstrations right now, looking at what do we need to put on the gateway that demonstrates a Mars habitat? What would you need to put in a Moon habitat on the surface? All of those things come together, and a lot of times when you talk mission architecture, we sort of focus on the in-space stuff of leaving Earth and getting to the Moon or getting to Mars, but the architecture includes what you put on the surface too. So that means, if you have a rover or a habitat, that's going to drive how long you can be there and what the crew can do. So the architecture absolutely includes those pieces on the surface, and there's lots of work going on and needs to continue going on in order to get us there right now.
Joe or Tim?
Yeah, I was just going to add, that's perfect. And the other thing in our study that we did at the workshop in November, when I mentioned ISRU earlier, a lot of people think about making propellant or making oxygen. We actually looked at materials for construction as well, and that's also part of in situ resource utilization. Use the regolith that you find there to build some of these structures. One of the things that we talked about a lot, our concepts now for both the Moon and Mars involve landing several times in relatively close proximity to one another. We know from our earlier experiences that we're going to blast things as the rockets come down. They sort of throw rocks, and so we're talking about building things like landing pads. and things like that. So it's all part of that. Yeah, you're absolutely right. It's all part of that bigger picture that we have to start thinking about.
And the only thing I'll add is, we do have some good experience designing zero-G habitats now, and we've been flying them in the space station for 20 years. Now we get to design partial Earth gravity habitats, and that's a whole nother field where in some cases, no different from Earth, everything works fine. In some cases, that partial gravity will make a difference. So that's going to be a good challenge up ahead.
Let's go to another question. Actually, this is a question that we're getting from a lot of our younger participants out there, and it's one I was going to try and get to before we finish today, but we'll do it now. I'll use it as it was submitted by Tonya. She is a student. She wants to know, she wants to be involved in space science and exploration, but doesn't know what avenue to take. Do you have advice for students on narrowing down our interests and finding the right career path at NASA or its partner orgs? And I'm going to modify that a little bit because we're getting similar questions, like one from Estefania Osequera. She's specifically interested in how do you get into this field of mission architecture? Do any of you have advice for these two and some of our other young participants?
I'll go first. And I think that there's two questions there. And the first question is, how do I get involved in general? And NASA and industry, we need every type of person to be involved in spaceflight. We certainly need the engineers and we certainly need the scientists, but we need the communicators, we need the artists, we need the business people, we need the strategists, we need everything. And so if you have a particular passion, whatever it is, and a passion for spaceflight, there's no reason that they have to be separate. Bring what you're great at and develop that and come join our community in one way or another. And we'll welcome everything. And then on this, to me, the specific question on the mission architecture part is, I've got lots of people on my team and Najud's team and Joe's team with different engineering backgrounds. Some of them come from the structures, some of them come from guidance, navigation, and control. And a lot of people come from the trajectory side, but it is really a multidisciplinary thing. So curiosity is important in learning about how things have been architected in the past. And then also what's very important is doing the day-to-day work on a program before you are in one of these roles, so that you know what it's like to design a mission and have the nominal mission and 16 different off-nominal missions and all the pain of doing that, such that you're prepared when it's time to think of the big picture to understand all the little details. And then you get to take off that detailed hat and think like a fourth grader again. And if you've got the right background, then that's the perfect mix.
Joe, Najud, any advice?
Well, I'll just echo what Tim said. Everyone comes to this field from a different background. And I mean, I have the job I never knew I always wanted. Because, I just wanted to be in space and it's so cool. And like, I wanted to be a part of specifically human space flight. So I started on the space station and guidance and control and things just sort of evolved. And really my interest has always been solving those big picture problems. So first you solve them on a small scale. I did it at a system and then sort of at a vehicle level and now sort of at the architecting level. And that's just because my skill set is the solving of problems. And so you come in and you solve those issues and you need the knowledge of the spacecraft, like Tim said. You need to know how it actually works and comes together and how the operations works and how the crew needs to interact, because you can't just step into this and go, I can design the perfect mission to Mars. Everyone has to come from somewhere and it all is a big team. So you bring your niche and your capabilities and that could be business, it could be finance or trajectory design. And then it all comes together again. And you just have to work your way into it because you need that depth of knowledge.
Joe, who or what do you look for when you're hiring people?
I think everything that's been said is absolutely true. And I'll just try to say, one of the things that I've seen is passion is absolutely a critical element. No matter where you're coming from, no matter what your skill sets, if you have a passion for this, you'll find a place in the industry. I think the other thing for systems engineers especially, you can come from a lot of different engineering backgrounds. Some people don't even have engineering degrees. You need to have a curiosity. You need to be interested in where does this piece I'm working on fit into the bigger picture and what's on the other side of the wall. You know, you're not just working in your little cubicle and throwing your job over the wall when you're done. You want to know where is it going and how does it fit together, and all those things that Najud said earlier, all those pieces that have to come together. So those are good systems engineering characteristics. And then the last thing I was just going to add was perseverance. And I'm not just trying to rip off the new rover name. The problem that you run into in this business, like in anything else in life, is you're going to hit some brick walls. And you can't stop when you hit that brick wall. You got to bounce off, you got to jump up, and you got to figure out how you're going to either get over it or get around it, or maybe you can, use the brute force method and go through it. But there's a lot of times in our careers where we've run into those things, and sometimes even the whole program gets canceled, and you have to find another program, but don't give up.
I've got us now at about 4 minutes past the hour, and as I said, we're in bonus time now. We'll keep going for a few more minutes with some of your great questions. And as always happens with these, they do tend to fall, many of them, into certain categories. So here's one that kind of represents what a lot of you are asking. This specifically is from Jeff Stewart. Crewed lunar missions concepts exhibit an evolution from boots on the ground, just getting there to get back, to sustainable and reusable infrastructures. Will missions to Mars show a similar evolution, or will they be sustainable, reusable right from the start? Who wants to take that first?
I'll take that first and just keep it short. Right. Yeah, absolutely. What we're trying to do on the moon is make sure it isn't flags and footprints, and then we don't go back for 50 more years. Right. We need to be able to build an infrastructure that's sustainable at funding levels that can be maintained over time, and architectures and equipment that's sustainable over time. And my personal belief is that as we go to Mars, we need to do the same thing, or we'll end up with another huge gap. If we send one mission to Mars and that's all you can piece together, then we're not doing it right. And we need to have a much better evolvable architecture for the future.
Yeah, and I would say that that the absolute goal is for them to do all that testing on the moon, and then for Mars to have everything be reusable. But I also know that when you get down to solving the problems, there might be some, unique thing about Mars that means, for entry, descent, and landing, or something that we're almost there, but not quite. We'll do a couple of missions, but like Artemis, then, we'll have that sustained, very reusable path ready to go after a few test flights.
How important has the International Space Station been to helping us learn how to maintain structures for long, long periods in space and make them places where humans can survive? Joe?
I think it's been, really vital. There's a lot of, I mentioned earlier in the human side, the long duration microgravity information we're getting now from things like the 1 year duration stays that we've had a couple of astronauts do now. We've certainly been able to put a lot more people up there into that environment. But then just taking another quick example, something like upgrades. We're doing the batteries now that are the new batteries for the station to replace the initial ones. The fact that we can actually go out there and take out those old batteries and replace them with new upgraded systems, that's a really critical thing for those future missions. Like Tim was saying, if we want to make these things reusable and have them be something we can use in the future for Mars for many, many missions, we need to be able to upgrade as better technologies come along. So I think there's a whole variety. That's probably just scratching the surface of things that the station's given us.
Najud or Tim? ISS?
Yeah.
Go ahead, Najud.
So adding to that, right? So some of the big things we learned from Space Station 2 was the international partnerships, the
Oh, yeah.
assembly
Yeah.
in space, you know, the ability to actually, we can't go to Mars with just one module. It's going to take several. So that knowledge of just how you assemble in space is something that feeds forward to the Mars, the Moon and the Mars architectures. And so there's so many things like that. Our partnerships, the assembly, the ability to integrate commercial now. So the fact that we have commercial cargo and commercial crew, which literally is going to launch this month, humans again, right? Those things are all like the how do we do things differently. Space station gives you that platform to test out commercial industries and stuff like that. And all of those things are already paying dividends on the Moon architectures we're looking at, and we'll do so again for Mars.
Yeah, I think that commercial and government space programs working together is an amazing lesson from ISS, such a success. I'm looking forward to seeing that plug into Moon and Mars. And I actually pulled up some stats that I just recently been sent, so I knew about them. One of the things for these missions is the logistics and keeping everything working, keeping all the supplies, and just the sheer number of launches. So since the end of April, there's been 222 launches to the ISS, and which is a staggering number, and 41 assembly flights. And so that really proved that the things that we're talking about at the Moon and Mars, it's not those amounts of complexity or launches. And so ISS really tells me that we can go do this. We've already done it.
I like it. We can do this. As I glance through the questions, and we are nearing the end of our time here, before we throw things back to Chris Carberry, there seem to be, maybe the biggest category is still with those human factors, considering things like medical care when you're away for 2 years without an MD, although who knows, maybe there'll be an astronaut MD. Food, which is something we took up in the Life on Mars discussion that I had with Jim Green and Penny Boston. But let's focus on the medical services and, you know, keeping people alive and healthy. Is this something that you folks as engineers and mission architects, is this another one of those many factors that has to be integrated, how we're going to, you know, keep people healthy enough to explore Mars? I don't know who wants to get in on this.
I'll say absolutely, right? You know, we have a lot of requirements that come from, you know, all that history we have. We have 50 years of human spaceflight history, more than, and all of that drives, you know, how big is your habitat? How much is the food you need? What can you do differently with the food? So we have way more advanced food techniques today than what Apollo had, which, you know, was a sandwich in a bag in some cases. So, you know, we can do a lot more now. The astronauts spending a year on the space station, how do you keep them healthy? Telemedicine, all of these things are techniques that we need to get to Mars, because you need to really pack down how much stuff you have to take. So all of those challenges we continue to work on today, and there's still many challenges for this.
Yeah, and I would say another thing in our workshop that we addressed was not just the physical health issues, but also the mental health issues. So, you know, I guess the isolation you talked about, Matt, in the previous webinar that was done by Explore Mars, but also things like, you know, how much volume do you need for a habitat? Because people need so much space. You need a little bit of time to get away from everybody else when you're out there. Even if you're the, you know, best crew ever, that you all really like each other, it's probably going to get a little tough. And Najud said it earlier really well. We're all kind of going through that right now in our own individual houses here. But, and then the other thing I was going to say is AI. We talked about artificial intelligence a little bit earlier. I think a lot of that, both telemedicine, but also because of the latency time, you know, for the Mars missions, some of this may be dealt with an onboard computer that has a lot of medical information stored in it, so that the astronauts can call that up if an incident occurs.
Yeah, what if the doctor is an astronaut and she gets sick? You know, it's not just one doctor. Every crew member is going to be cross-trained in everything, because they're going to need to rely on each other, and even more so than they do today.
One of the most interesting and unexpected conversations I've ever had with anyone on planetary radio was with a woman who is a dentist, who was speaking at a conference about what happens when one of your astronauts halfway to Mars gets a terrible toothache. Who's going to take care of that? And be sure to floss, everyone.
Wrong set of pliers.
Could be. We probably should wrap up here and get ready to go back to Chris, but I want to give each of you a chance to sort of sum up here. And in some cases, it's going to be repeating what you've already said, which is about, are we on track to achieve this through the kinds of great systems engineering and mission architecture efforts and the development of all the technologies and other factors that are going to get us to Mars, hopefully, before another 15 or 20 years goes by. Jude, why don't you start us?
Well, I'll just start to say, I think there's never the only other time that could have been more exciting. This was 1968 when people were actually going around the moon and about to land, right? But as of today, we have real hardware, real rockets, real spacecraft, and we are really going to the moon. And I know, people don't quite believe that till you see the smoke and fire and it takes off. But I couldn't be more excited about the future we have right now, because we have a real plan and we're building the real stuff that's going to get us there.
Joe, your turn.
Yeah, I'll pick up on that and say I agree with everything. And we also have characterized a lot of what we don't know, so that in this business, we put together what we call risk cubes, and then we identify what we need to do to burn those risks down. And I think we've got a lot of that information pulled together now. And, I'll just say back to what we said before, I think all of us said we're going to go out there to the moon with Artemis. And that's going to be part of that process where we start burning down that risk. And I think in the next 6 or 8 years, we'll get pretty far along on that, to the point where we're much more comfortable to say we're ready to go to Mars.
Tim, take us home.
So one time I was able to be in mission control during an ISS mission, and as a shadow, looking over folks' shoulder to understand. And the fire alarm went off on the International Space Station. And it was in the middle of the night, and that control room snapped to attention, and they were ready to evacuate the space station. And I thought about, well, if you're halfway to Mars, or you're on the surface of the moon, you just can't, go outside when the fire alarm goes off. And that shift in thinking that's happening right now is maybe the most important part of mission architecting, is to realize this is such a challenge and we've got the tools to go solve it. Let's think differently and let's go solve it. And so, yeah, the next couple of years is going to be an amazing couple of years where we're going to be back at the moon on our way to Mars.
Hear, hear. I hope that all of you out there have enjoyed this fascinating exploration of mission architecture as much as I have. I've learned a lot, and I feel pretty good to know that these are 3 of the people who are going to make what Ray Bradbury told us so many years ago true, that we are the Martians, or we will be the Martians. With that, Chris, I think I'm ready to turn it back over to you, and I will just thank you, Chris, and Explore Mars, for letting me host this discussion, this great conversation. And I so look forward to, first of all, watching that one with Frank White, the originator of the overview effect on the 13th, right? Wednesday of next week. Sorry about that. And then I look forward to coming back and having a conversation with John Grunsfeld, 5-time visitor to the international, I get it right, 5-time shuttle, 3 times to the Hubble Space Telescope, and that will be our topic when we talk on May 19th. Chris, get me out of here. I better stop talking.
Well, thank you, Matt. That was great. And thank you to Jude, Tim, and Joe for a spectacular session. And thank you to everybody who came on. We had a really great audience today. And so I just want to remind you about our upcoming webinars coming up. As Matt mentioned, next week on Wednesday, May 13th at 3 p.m., we have a session called The Overview Effect with Frank White, and that'll be moderated by Mary Liz Bender and Ryan Chalinsky from Cosmic Perspectives. That you can register for that now on the Explore Mars website, ExploreMars.Org. Actually, I saw a number of registrations come in right during this webinar, so people are already registering. And on the 19th of May at, I believe we had 1 o'clock Eastern Daylight Time, We're going to have John Grunsfeld on, 5-time shuttle astronaut. I believe he visited the Hubble Space Telescope 3 times. They call him the Hubble Hugger, and Matt will be moderating that. So more information will be posted on that very soon. Then 2 days later, on the 21st of May, I believe at 1 o'clock, also, we have Star Trek actor and director Jonathan Frakes, Commander Riker from Star Trek Enterprise. He'll be joining us to talk about entertainment, space, collaboration between the space industry, space entertainment industry, and STEM education. So that'll be a great one as well. And we have a number of others being lined up over the next few weeks. So please join us. So thank you once again, everybody, for coming on, and we will post all of this information very soon. We hope to see you next week. Have a good day.
Thank you.
Take care,
Bye.
everyone. Thank you for
Bye,
joining
everybody.
us.
Thank you.